Thank you, Doctor.
Just let us know when you would like us to start. Like people are still joining.
Yeah, we can start in 5 minutes. Okay.
Okay. Adina, will you start with a few words or?
Yeah, I will just take a minute and then hand it over to Jana.
Okay, thank you.
Just give them another couple minutes and then I'll start.
I guess, Doctor, we can start now.
Hello and good evening, everybody. Thank you for joining us for the lesson on socioeconomic dimension of the water energy fuel nexus with a presentation about the Bristol, UK case study. The lesson today will consist of 3 presentations from members of an international collaborative project that was funded by the Belmont Forum. The name of this project is called Waste Fuel, and the goal of that project is to reduce the waste and develop internationally applicable methods to identifying inefficiency in food, energy, water nexus. The project or the whole program works around 4 urban living labs, and they're in different countries, in the UK, Bristol, in the Netherlands at Rotterdam, South Africa, around Cape Town, and in Sao Paulo, Brazil. And today you'll hear from 3 members that were core component of the Bristol ULL. On Tuesday, you'll hear from other representatives of this project. So with that in mind, our first speaker, Dr. Jana Fried, who is from the Center of Agroecology and Water Resilience at Coventry University in the UK, will give us an introduction about the Waste Fuel Project, and will focus on approaches to identify promising nexus connections or how to engage stakeholders. This will be followed by a presentation by Mr. Ali Parsa, who's a PhD candidate working on system dynamics modeling. And last but not least, Dr. Eleanor Eaton from Bath University will be sharing information about non-market valuations relevant to Bristol's ambition to reduce food waste. So you will see that you will get introduced to different methodologies that are relevant for the water, energy, fuel nexus, including stakeholder engagement, system dynamic modeling, and non-market valuation in the context of employing urban living labs. So with that, I will let Jana take over, and she can share her screen, and hopefully if you have questions, please put them on the chat or raise your hand so we can address them. Thank you.
Alan Mesael here, Salam Alaikum. I hope I managed to say welcome and good evening, and that I am really looking forward to sharing this lecture with my two colleagues, which Adina just mentioned, and I hope that the sharing of my screen will work. Wait just a second, because I did open the screen sharing. Is it currently sharing or not yet?
Not yet.
Okay, so somehow this got stuck as usual when you do something like that. Let's try it now. There we go. Now this looks better. And I shall put it on full screen mode in the hope that it is easier for you to read. How is this currently?
That is presenter mode still.
Yep, I'll try this now. How is it now?
Still presenter mode. We see your sidebar with the PowerPoint slides.
Because on my screen it actually showed. Okay. Any suggestions of what I need to change then?
If you go to your screen on the lower right side, just press still share that, but just press on your screen the full presentation.
Yeah, I had done that. That's why I was surprised that it didn't do it. Anyway.
Share it again. If it doesn't work, we can live with the sidebars.
Let me try it now, what it does now.
You can press F5 directly. Press F5.
Is it working now?
No, there was a suggestion to press F5.
Okay, F5. Let's try that. Any difference? Because I actually, on my screen, it looks like it's the full presenting mode screen. That's why I'm a bit surprised. Okay, but you are not seeing that, do you?
We're seeing the slides, but also with the sidebar on the left with all the other slides, which it's probably fine.
Okay, let me see how I can make it just bigger before I waste any more time.
Jana,
Yeah?
I think you need to share, when you press the share screen, I think you have two options: sharing the whole, your desktop or the whole Windows, or just one presentation. So if you choose presentation, I think the problem will be solved.
Okay, let me just do this now. I think it's hopefully better than it was before, even so it's not perfect. How is this?
Better.
Okay, all right. This is not
Yeah,
quite
that's great.
thought it would be, but it's fine. I mean, at least you hopefully can read things. So as Adina was saying, we are going to present examples from the waste fuel project, which was, as Adina said, an international project. And on the left side in this little map, you can see some of the partners really across 4 continents, Africa, Europe, South and North America, with living labs in 4 different areas. We had a living lab in Bristol, the one we are going to talk about today, but also in Rotterdam in the Netherlands, in Cape Town in South Africa, and in Sao Paulo in Brazil. And as Adina was saying, you will hear more about that. What was special about this living lab, maybe differently to some other Nexus projects, is that we specifically focused on waste flows. And the image on the right side is meant to illustrate that, how waste, which we obviously want to reduce across the board, can actually become, when it's a waste in one sector, can actually become an input into another one. And therefore the overall waste across the Nexus is being reduced. And so as you can see, the project aim was trying to really look, how can we decrease resource inefficiencies? How is it now working? One of the, sorry about that. One of the big questions here is, we are talking about urban living labs. So what are actually the advantages of thinking about implementing sort of research projects, but also real world projects at a living lab scale? And I do want to point you to a website, which is called the ENNOL, the European Network of Living Labs website, where they are really having a lot of resources around living labs. But just as a background, living labs are really places where within a real world setting, different stakeholders, multi-stakeholders can come together using multiple methods in a real life setting to actively include users and co-create new technologies, new ways of working. And thinking about the Nexus, this seems to be a really useful approach, because trying out Nexus technologies within a, let's say, lab setting at a university is very different than if you actually do so in a real world setting.
Jana, your slides are not forwarding.
Okay, so what are you still seeing now?
The introduction, first slide.
Okay. I'll try that again. I don't know what's going on there. I've never had these issues, because I usually manage, but let's see how that works now. So I was told F5, is that right?
You're sharing okay, just try to forward there. Now you see the Nexus at a steady scale slide.
Okay, so looking at
now we're at your slide 5.
Okay, looking at, that's perfect. Looking at the Bristol Urban Living Lab, I wanted to just point out, we had a multitude of stakeholders involved in that project, and I don't want to spend time reading them all out or explaining them. But it really was one of the challenges. How do you actually engage that many stakeholders? And that's what I want to briefly talk about. As a background, Bristol in the UK is situated in the southwest corner. So you can see there of the country, is the biggest city in that area. We have 500,000 people, about 500,000 people living there. And it's a really major economic center with, and that's really interesting and relevant, ambitious targets towards sustainability, including, and that's a big one, which also is relevant to the 2 other presenters' work, reducing food waste quite dramatically in the next few years and decade. And so that's, as a background, really important where we are situated with the work we present here. these are the stakeholders. How do you actually go about engaging with them was one of the things, but also what are key challenges when you're and tasks when you're thinking about the Nexus at a city scale. As I mentioned, the Urban Living Lab is a useful approach for that, but it's quite tricky to know when to integrate stakeholders, who the stakeholders are, how do you connect with communities, and how do you really get the buy-in when you want to change quite dramatically services within a city, processes which are really affecting local citizens. They are not just sort of abstract processes which maybe certain service providers are involved in, but actually really have major implications potentially. And so one of the questions is also, what are the boundaries that need to be included when we are thinking about an urban living lab? And so this is something I wanted to just point out, that different sectors have different scales, geographical scales in which resource flows, financial flows are taking place. So that was one of the challenges and interesting things to consider when you're thinking about the Nexus in a city. But as I mentioned, one of the key areas we also found challenging is how do you actually identify who are the stakeholders you need to involve, what are the organizational connections, the resource and financial flows, and what are key opportunities for Nexus thinking at a city scale. So when you go beyond a smaller experimental project potentially. Some of these approaches, I just want to mention most of them here because of time constraints, but you will hear about system dynamics modeling and the economic modeling. One of our colleagues and also a PhD student on the project looked at social network analysis, a really useful approach to really identify who are the key stakeholders and how do you, what are the connections? How do they interact at what point? What we've done is maybe a relatively easy to implement process, and that's why I think it might be useful to introduce you to this. It's a participatory mapping approach where we had identified key stakeholders based on the partners in the project who were really key actors, and then used a snowballing system, which means that we asked them who are other important stakeholders to identify who we should invite to this participatory mapping process. And what we've basically done, we've run stakeholder workshops across the three sectors of water, food, and energy, inviting key individuals, key organizations to come to those sector separate workshops. And then we run through the identification of current and future linkages at the Nexus level. And then did a deep analysis. I'll just show some of these activities briefly for you. So we had these workshops where we asked people to think individually. How do you identify what are the Nexus connections you see from your sector? Let's say in this case, the energy sector to food and to the water sector. What are these connections? What we then did is we collated all the different ideas and notions, having asked stakeholders to identify existing connections, but also those which they see as possible in the future. And so we then went to present them from everyone, collated them, clustered them. And I will show you that in this picture. So we put different ideas together and identified overarching themes. So in this case, these different stickers you can see here are all ideas of Nexus connections under the topic of nutrient recovery via water. And with these topics, this is another one, water input into the food chain. So we were thinking about how water and food is connected. With these connections, we then asked the different groups and stakeholders to work through some of the, to identify some of the key actors within, let's say in this case, nutrient recovery via water. What are sort of key opportunities, what are key challenges? And you can see that in this graph. And what we've then did after we've worked through this in depth, we presented it and discussed it to really see what are the next steps going forward if we wanted to sort of dive deeper into some of these topics. Then we analyzed all the results, captured them in this way where you can see on the topic, these oval headings are basically showing you what are the key topics that emerged from the food, the water sector. We also had the energy sector. And then you can see what are the ones which currently exist, the Nexus connections which exist, and what might be future ones. And just one of these images of the deeper analysis of some of these Nexus connections, what was going on there. What also emerged from these three sectors when we did the results of all three workshops together was that we had some topics which really the water, food and energy stakeholders all identified as interesting and something for us to work at and look deeper into. Some of it is around the reduction of environmental pollution, specific technologies like anaerobic digestion flows, land use questions. But then we also had something more overarching like behavior in the Nexus or the value chain. All of these topics were things we could actually run separate research projects on. So in some ways, these were really key results to just pinpoint what are the opportunities in Bristol, where could we work on, and where would there be a shared sort of appetite within the three sectors to really sort of move into and change what is going on at the moment. And so to summarize a little bit, stakeholder engagement is really an opportunity, but also a challenge, but it helps to identify Nexus stakeholders. It starts building relationships of different actors and organizations and to develop common vision and goals. And it can be a first step to deal with hierarchical complexities, organizational complexities, and to build connectivity and sort of analyze the dependencies of economic and resource flows as well. And just to repeat, I believe that urban living labs are really a great opportunity for Nexus implementation. And these results, which we had then also went into the next steps of modeling, including the systems dynamic modeling, which is what Ali is going to present about now. And I have to apologize that because of the technical problems, I had to speed up a little bit, and I believe I still run over time. And I hope we have some time at the end for some questions, but I would like to pass on to Ali now because of the time constraints. And yeah, have a nice day still, and to see you at the end for the questions.
Ali, do you want to take over and share your screen? And I suggest we save, unless there's clarification questions, we can save the questions to the end and talk to both Jana, Ali, and Eleanor about how this reflects on the context in Egypt or any other questions specifically that you have. So you can go ahead, Ali. You're sharing your screen, okay? You just need to go to presenter mode.
Okay. Yes. So can you see my
Yeah, we
presentation
see
full
it
screen?
very nicely. Thank you.
I can't hear you, Adina. Just can
Ali,
you confirm it?
yeah, we see your presentation.
Okay.
You can also introduce yourself, tell people where you're from so they know.
Yeah, of course. Thank you very much, Adina. Thank you, Yana. And hello, everybody. Assalamu alaikum. My name is Ali. I'm from Afghanistan, and I'm a third year PhD student at Coventry University. My research is about system dynamics modeling of food, energy, water, and climate nexus in urban circular economies, which basically, just to start with, I would love to start with a little bit introduction into the main concepts that I'm gonna discuss in my research. So the first one is circular economy. What do I mean by circular economy? Circular economy is a model of production and consumption which involves sharing, reusing, repairing, refurbishing, recycling of materials and goods and products as long as possible. And actually, the concept of circular economy is in the opposite of the usual linear economy model of linear model of the economy that we have in most of the societies, which is based on extract, use, and finally throw it into the waste or dispose it, which is opposite. In opposite to that is the model of circular economy, which focuses on three basic principles. Which the first one would be designing out waste and pollution from the whole system. The second one is keeping products and materials in use as long as possible. And the final one is to regenerate natural systems. So by food, energy, water, and climate nexus, I basically mean the study of the connections and interrelations between food, energy, and water sectors in order to identify the synergies and trade-offs in this system, which then can be leveraged and managed for waste reduction or material resources reduction. And as you can see in the middle picture, on the right-hand side picture, there are several interconnections between food, energy, and water resources. For example, for food production and food consumption, we need water and energy. We need for energy, we need water in various different stages of the energy production, and for water resources, the food and energy has some impacts on the water resources, which basically means depleting the water resources or contaminating the water resources. So as part of my literature review, which is now published as a paper in Journal of Cleaner Production, I have combined these two approaches, I mean circular economy and food, energy, water nexus approach together, and created an integrated approach, which basically means how we can use both classes together in order to make a perfect or probably more comprehensive approach for studying the food, energy, and water systems. By urban, specifically, as you already heard from the speakers, there are three, actually for my case study, for my work, there are three urban areas, which we call them urban living labs. The first one is Bristol, the second one is Rotterdam, and the last one would be Cape Town. At the moment, my focus is on the Bristol Urban Living Lab. And in this specific research, I focus on food system, hoping to do the rest, I mean energy system and water system in the other ULLs. So what you will see today is the outcome of my research on food waste minimization in supply chain in Bristol area. And in one hand, and on the other hand, food waste management impacts on energy, water, and climate systems in Bristol. System dynamics modeling is the method that I'm using, and to define it and to explain it is a very useful method, which basically uses computer simulation to build models, and these models then can help us to understand the nonlinear behavior of complex systems. For example, the food waste over time, and this basically means this the system has a structure which defines its behavior over time, and this method can help us to find that and to learn that behavior by studying the structure of the system. There are basically, I can say there are three main building blocks of the for the method, system dynamics modeling. The first one is the stock, which, as you can see, the rectangle in the picture is a stock. You can imagine it as a bathtub or as a container which accumulates something, anything. The flows and the flow of anything can be accumulated in the stock, and there could be an outflow of that stock, which makes the system as in a feedback loop. The feedbacks occurs when outputs of a system are routed back as input as part of a chain of cause and effect that forms a circuit or loop. So regarding the feedback loops and the stocks and flows, here you can see a causal loop diagram of my model, which is a lot of loops, a lot of elements in that. I'm not going to through each of them, but this causal loops basically says that how the system structure can affect the behavior of the food waste. And starting with two of the main governing loops here, for example, the one of them is population growth, which basically means that when the population of a city like Bristol grows, the food consumption and the food waste grows as well. So this is like one of the main reinforcing feedback loops. And the second one would be the same story about the growth of hospitality and food sector, hospitality and food services sectors, as you can see in the R3 or reinforcing loop 3, number 3, basically says that when the economy grows, the hospitality and food services also grows, and this leads to more consumption in the hospitality sector. The other loops there are many other loops which you can see in here, but some of them that I'm going to study here is the redistribution loop, for example, which basically means that when you redistribute the food surplus of the commercial sector to people, the people need to buy less food, and by that there is a balancing loop. Or for example, reduction, we have reduction waste loops, which basically means that when you reduce food waste, you will need to buy less food, and this is another loop. Or for example, AD loop, as you can see, anaerobic digestion and energy production loops, which I'm going to discuss them throughout this presentation. Here is a very kind of messy model of my food supply chain. to simplify it, to say it in a very easy words, the agriculture sector produces food for Bristol, which some of which goes to waste. This food is then taken to manufacturing, to be manufactured in the manufacturing plants, which then again some of it goes to waste. The food from manufacturing goes to retail and wholesale sector in the shops, supermarkets that we can see, and some of them, some of the food from that sector also goes to waste. Finally, the retail and wholesale sector sells the food to people, either to people or to hospitality sector, both of which generate food waste. When the food is wasted, it can be treated in different ways. Some of it, or probably it's better to say the food surplus because it's not wasted yet. Some of it can be used and for human consumption and animal consumption, which we call it food surplus. Some of the food surplus, as you can see on the left hand side of flow, some of this food surplus goes for human redistribution, and some of it goes to animal feed. The rest is kind of combined with Bristol food waste, as we call it wasted food. And this can be either composted or goes to anaerobic digestion if they are separately collected. If that food waste is not separately collected, it goes to incineration. It can be used, it goes with general food waste, general waste or residual waste, which then can be incinerated in the incineration camps, burned and generate energy, or it can go to landfills. These are my water footprint, energy footprint, and carbon footprint modules, which kind of tells the same story. In food production, agricultural production, manufacturing, retail, households, and hospitality, in all of these steps, we generate food waste. Also, we consume water and energy in each and every level. And in each and every level, obviously, we emit some carbon dioxide. Here are some results of my work. So one of the main purposes of this modeling was to see that which one is better. I mean, is it better to reduce food waste, or is it better to redistribute food surplus from commercial food surplus and waste to people, or other waste management options? Here I compare the food waste reduction and redistribution with some specific assumptions. First, my first assumption is that the food waste reduction is 5% per year, as you can see in the left hand, upper left hand graph, and the food waste redistribution on the upper right hand. They both have the equal amount of reduction or redistribution, so the percentage is equal. And because the model is run for 20 years, it means that 100% of the food waste either is reduced or redistributed. In the bottom side, you can see the food footprint, energy footprint, carbon footprint, and water footprint as a result of the modeling, and how these different policies affect the whole food footprint, as they call it. So just on the left bottom lower, you can see graph, you can see that run number one is business as usual, which shows that the food waste, the food waste is kind of steady throughout the time. Number two is the food redistribution, and the number three, the number two is the food reduction, and the number three is food redistribution. You can see that if the food is redistributed, 5% food is redistributed, you can see relatively lower food waste than the food waste reduction. On the other hand, you can see the energy footprint of the food redistribution is higher than the food waste reduction. The same story happens to carbon footprint and water footprint. This can help us to conclude that food waste reduction is environmentally better, the best option so far, comparing it with food waste redistribution. Here, again, I worked on another scenario, which for household food waste, I decided to model 5% food waste reduction and compare it with 5% food waste redistribution, 5% composting, 5% incineration, and the same amount for AD plants. As you can see, the 5% reduction, which is the red number two, run number two, you can see that the food footprint, energy footprint, and carbon and water footprint is significantly lower than the other options. One interesting thing is the 5% redistribution, 5% food redistribution, which, as you can see in the water footprint on the right-hand side graph, that it has a significant impact on the water footprint, which is very good. But in terms of AD plants, sending food waste to AD and incineration, you can see there are slightly more energy and carbon footprint, which basically means that the more food waste goes to incineration plants or AD plants, they generate more energy and they reduces the carbon footprint. If you zoom into the energy footprint and carbon footprint, you will notice that the energy footprint of AD plant is lower because AD plants generate more energy than incineration plants. And also the same happens to carbon dioxide, which means that AD plants reduces the carbon footprint more than incineration plant. So this basically kind of focuses on and echoes the food and drink material hierarchy, which you can see on the top right. And this says that the food waste prevention and reduction is much more environmentally better than redistribution, and then recycling, and then recovery, and finally disposal. So as to summarize my work here, first of all, the total food waste of Bristol in the supply chain is around 93,000 tons. One of the advantages of this modeling practice is that you can estimate and you can calculate the amount of food waste in different sectors, and the total food waste in Bristol, which is around 93,000 tons. And this is around 1/4 of the total food consumption in the Bristol. This basically means that for 1 kilogram of food which is consumed in Bristol, 1/4 of that, 250 grams, goes to waste in anywhere throughout the supply chain. The second point is that food system has a significant energy, carbon, and water footprint.
Excuse me, Dr. Ali.
Yes.
How do you calculate the waste from 1 kilogram of consumption?
Is basically I can show you in the model, but the food waste is the total food waste is the sum of food waste in agricultural production, food waste in manufacturing, food waste in retail and wholesale, food waste in hospitality, and food waste in households. So if you sum them up all together, you will find this 93,000 tons. I hope it answers your question. And I'm going to share my model if we have enough time, which I'm afraid we don't have, but I'm going to share my model
Eleanor,
later.
do you have time, Eleanor?
Yes, I think it would be interesting to see.
Yeah, just to summarize it, to finish this. So the second point was food system has a significant energy, carbon, and water footprint. This is very interesting to see that the food system in Bristol, the energy footprint of food system in Bristol is around 20% of the total Bristol energy. The 53% of the carbon footprint of Bristol, and 10% of the water footprint of Bristol. The other point is the modeling results echoes that, as I just mentioned, the prioritization of food waste hierarchy framework. But there are, if you zoom into that, you can see that there are some exceptions or some minor changes or dynamics over time. For example, when you reduce food waste at household level, or when you redistribute food waste, you can see for a specific amount of time, you can see that the food waste of the upstream, and by that I mean food waste in agricultural, manufacturing, and retail, goes up. The reason for that is because the food stock in agriculture, manufacturing, and retail gets fuller, and they waste more food. These kind of dynamics are very interesting, which can be seen through the system dynamics modeling. And finally, I found the system dynamics modeling a very interesting and useful tool, which helps us to understand the very complex food waste system in Bristol. And I definitely suggest you to look at the method and to see if you can use this method for your own purposes. Thank you very much. And again, if we have time and interest from people, I can go through my model later and show how it works and what are some of the interesting results.
Ali, can you quickly tell us where or how you assemble the information to turn the model to quantitative amounts? How much information is needed and where do you get it? If people want to use the model in their context, how much legwork do they need, and what kind of access to information do they need to actually know how many tons are being used or consumed and what is the waste in that?
In terms of modeling itself, so in terms of data, I gathered my data from all different sources around for Bristol and for the UK overall. And if I couldn't get some specific numbers, I even got some data from international and worldwide organizations. Well, in terms of the details of that model, to be honest, if you need to, so first of all, the detail of the model doesn't necessarily tell you the accuracy of that model. You can have a very detailed model, but your results could be flawed. So that's one issue. And the good thing about system dynamics modeling is that you can build up a very nice, useful model with as much with few stocks and flows, which is interesting. But for my model, to be honest, it's more than 1 year that I'm gathering data and I'm playing with the model, and there are lots of variables in that. So which hopefully I hope that the results are more valid and reliable.
Thanks, Sally.
Yeah. Okay.
So how about we let Eleanor share her presentation, and then at the end we'll have questions for all of you. And if there's time, you can share the model.
Okay. I think I might have the same problem. I'm trying to get my thing to share.
I think if you go on the bottom right side, there is this,
Oh,
yeah, that place.
Good point. Well, thank you. Honestly, Zoom is a different technique for every platform, isn't it? I'm just getting familiar with that. So thank you, everyone, and thank you so much for the opportunity to be able to talk about our work. I'd lucky enough to have a really interesting piece of work as part of this project. We only focused on quite a narrow part of the aspect of the food, energy, water nexus, exploring food waste in Bristol. My name's Eleanor Eaton. I work for the University of Bath, and my interest is in the economics of how aspects of the environment affect human health, particularly. But in this case, what I was looking at is all the socio-economic and environmental implications of food waste. So, so what I'm going to be talking a bit about just is the situation with food waste in the UK. Looking at total food waste in the UK is almost 9.5 million tonnes, and that's an estimate because we don't really know how much food gets wasted at the farming sector, so right at the beginning of food production. But we know that households, rather than manufacturing or retail and wholesale, just households themselves waste about 6.6 million tonnes of food per year. And of that, 4.5 million tonnes could have been eaten. So we know that a certain percentage of food is inedible, things like fruit and vegetable peelings, perhaps, or animal bones. So, but it still forms a really significant part of food waste in the UK, which is just the carbon related to that food is equivalent to 10 million cars on the road. So, or 1 in 3 cars on the road. So if we were to reduce all food waste in the UK, it would be a massive impact. So we know that UN Sustainable Development Goal, or one key UN Sustainable Development Goal, is to halve food waste by 2030. And in the UK, there's a voluntary commitment by food producers to this 20% per person reduction in food and drink waste in the UK. So that 20% reduction informed my scenario building for what we tried to do here, to just explore some of the impacts of food waste in Bristol. So just what to cover what I'm going to cover very quickly about how we value impacts on the environment and why we might do that, and then explore how we first of all understand the resources that go into food and the resources that are produced, the resource flows coming out of food waste, by understanding the life cycle impacts of food waste, and then how we applied that methodology to understand the case study in Bristol and to derive our results. So I'm going to go into a little bit of that and then talk about some of the limitations of our approach as well. But just to start with, first of all, we had 2 relatively simple questions, which was the first was, what are the non-market and socio-environmental benefits of reducing food waste along the food waste cycle for Bristol, and what reductions in energy and other resource usage in food production, transport and waste disposal might be gained from reducing food waste by 20%. So the first thing I should say is, why did we use non-market valuation as part of this piece? And one of those really was to understand the impacts that food waste have in terms of pollutants, what we end up with is talking about carbon and water use and things like marine eutrophication or damage to soils. How do we weight those, and how do we compare those effects and understand the magnitude of those effects when we're trying to compare different outcomes? So what we use is trying to use and apply economic valuation to those impacts in order to understand, to be able to put them in the same metric, to use one single metric so we can compare them. And part of that is using non-market valuation. So what that is where we try to describe costs which have no market value. And for this, the thing that I tend to use an example is the spoiling of a sacred lake or something like that, which has an intangible value in that it is sacred to people. The beauty and cultural importance of the area may be huge to the people that live around it, but in terms of its economic, in terms of the market value, you couldn't put a price on that. But if we don't put a price on that, what that means is then things start to feel like they don't have value in some cost benefit analysis. And what we wanted to do was to try and bring back that level of impact into that cost benefit analysis understanding. So what we use, instead of being able to use observable costs that we'd find in a normal market, so the price that people would pay for things, so instead we use stated preference techniques. So what that is we ask people for their preferences based on a number of different experiments. One of them is choice modeling. So we offer people 2 choices and say, which one do you prefer? Or we can give people a hypothetical scenario and say, how much would you be willing to pay in this scenario? So what we end up with then is a value for willingness to pay or willingness to accept for a change in environmental quality. And then we use these intangible costs in conjunction with observable costs in order to derive a value for the societal impact of environmental change. So this, just to take one example, this is for carbon and climate change. So the units that we end up with for food waste, what we end up with is units that describe, for example, the effect of global warming and climate change. And it's not just CO2, we would be looking at impact of other pollutants like methane. But what we do is then use one single unit to describe that. And here we use the CO2 equivalent. And we know that the valuation of CO2 is incredibly uncertain and is liable to change very significantly by 2050. So the value that we use is derived from a European study, which estimated the value of a reduction in per tonne of CO2 equivalent. And that the approach that they used wasn't to get rid of all CO2 in the atmosphere or what the impact of an additional tonne of CO2 might do to the whole planet, because that's almost indescribable. What they used was just the value of what it might cost to reach the targets for the EU to get to 2050 in order, in terms of climate, in terms of mitigating impacts and the cost of reducing emissions. So it doesn't include all costs of carbon. So for my second example, we have another impact value, which is human toxicity, which is expressed as a single pound per, in terms of pounds per tonne of a specific chemical here, which is used in lots of cleaning products. And this representative unit, what that shows is the sum of effects of lots of different pollutants on human health. And what we use for that value for human health, it's based on a single case of cancer. And what we use there is understanding the societal cost of cancer, of a case of cancer. So that would include things like medical costs, medical treatment costs, but it would also include an intangible cost value. So how much people would be willing to pay to avoid the pain and suffering associated with that illness. So the technique that we use to derive these, to estimate these resources that go into food, it is based on life cycle analyses. So I didn't use a model myself. I used this information, which is taken from a study from Tonini et al., who looked at food waste in the UK and explored it right from the changes to land use. And this is around the world. So wherever UK gets its food from, it's based on those impacts. And so they've followed that all the way through, from farming to processing to wholesale and retail, and then to the households themselves. And then as food came out of the households, how that was disposed of. And they use a fairly big databases. In this case, it's EcoInvent, which then give you the resources for different pollutants that go into these products all the way along the line. So for example, just households will get in the car typically to go to the supermarket, and that produces CO2, it uses energy, and that sort of CO2 is included in those kinds of calculations, for example. So what this study Tonini did was they gave us 10 different impacts of food production and food waste across several different sectors and across different points in the chain, which was really useful for me to understand. So then we could use that to apply that to the Bristol case study, because what they do is they estimate it per tonne of food waste right at the end of the scale. However, what Tonini use is grid energy based on the whole of the UK. And Bristol is quite different from the whole of the UK. So they base, sorry, not grid energy, they base it on waste disposal techniques used in the whole of the UK typically. So in many parts of the UK, food waste isn't collected by special collections. And so in lots of cases, it may go to landfill. Whereas in Bristol, that's very rare. So in Bristol, we have a very different pattern, whereby about half of the food waste that's collected at the doorstep is collected by little caddies, which are taken away specially to anaerobic digestion plants, which then convert that into gas and fertilizer. So, so I needed to tailor these results in order to understand the Bristol context. And in order to do that, because Tonini don't break it down by different waste disposal uses, I had to use a second study, which is this study by Slorek et al., who did unpack the unit costs for different kinds of waste disposal. So then I could tailor it to the Bristol context. So they separate out the different environmental impacts of anaerobic digestion versus, they call it here CHP plant, but what that means is like an incineration plant where normal domestic rubbish goes, if it's not separated out into these little caddies, and then to understand the impact of that. So what they did was then give us this piece of information, which is slightly more than Tonini. They use, I think they have 13 different outputs of 13 different pollutants that they measure, and they compared all those different outcomes. And part of that was understanding the positive outcomes as well. So in terms of both incinerating waste and anaerobic digestion, both of those things actually produce energy. And because of that replaces grid energy by burning fossil fuels. And so because of that, many of these outcomes are actually negative in terms of that it actually has a positive impact on the environment, some of these waste disposal things, because it's reducing the use of fossil fuel generation. So what I did was take those life cycle analyses and then apply it to the Bristol context in order to try and understand what was going on here. So what we did was, first of all, we had to spend a lot of time with our stakeholders in order to understand the levels of food waste, how they were collected, and how they were disposed of. So in the UK, there's a big database of all waste that's collected by the waste companies, but we know that that's only a part of what actually happens to food waste. So quite often people put food waste in their compost in their garden, and spread it on their own gardens. And they also pour a significant amount down the drain, and that goes into the sewer. And we have less data on that. We only can derive data from that from behavioural studies using small sections of the community to understand that. And that's based on self-reported information as well. So we have to kind of guess at those estimates. But then what we're able to do is, once we're able to derive that information about what happens in Bristol and how much food is wasted, we were then able to understand using those life cycle analyses in order to understand the environmental impacts of food waste. And then we're able to put a value to that using our different unit costs for each one of those pollutants. So we have some very simple assumptions. We assume a linear dose response relationship between quantities of food wasted and environmental impacts. In real life, that we would see there's been many more interactions between all elements of the system. And I think, you know, Ali's presentation showed that that there is a slightly more complex thing going on in real life. And we don't model for market effects such as changes to food and waste disposal pricing. And some of that was dealt with by our colleagues who looked at a macroeconomic patterns of food waste and to try and understand that picture. So we only wanted to just really focus on this micro aspect of just simply looking at the environmental impacts of food waste. So and just for clarity, that I'm only presenting the central values here, so I'm not showing the ranges of uncertainty, but we go into more detail in that in our paper. So just to say a little, I've explained a little bit about how Bristol's food waste is treated. So basically, we have food that goes into, typically on a household, at a house, you'd have a black bin, which is like all domestic rubbish gets thrown in there. And that black bin is taken away by a truck, and that's taken away and incinerated. And secondly, we have these little caddies for food recycling, and not every house in Bristol has that. So it's only a slightly smaller proportion because blocks of flats and things like that don't use this service. And that food is taken away to a separate site, so an anaerobic digestion site. So yeah, so this isn't typical in the rest of the UK. In some places you have to pay to get food waste taken away, and in some places there isn't that service at all. So it does vary across the UK. So just a little bit about where Bristol's waste goes. So we understand that around 48,000 tonnes of food waste was produced by households alone. So Ali was looking at a kind of slightly wider picture there of all food waste. So we're only looking at her homes rather than like takeaway restaurants and that sort of thing. But we could understand that about 41% of food, wasted food, goes straight into the domestic black bin along with other kinds of rubbish. So only a very relatively small proportion of food actually goes into these food waste recycling caddies. And we think about 23% of all waste actually goes down the drain in the form of things like milk, orange juice, those kind of things. We around 72% or 34,000, just over 34,000 tonnes of food could have been eaten. And that's equivalent to about 3.3 kilos of avoidable food wasted per household per week. So that's about equivalent to the rest of the UK, but Bristol recycles much more of its material. And what we did in Bristol, our stakeholders were very keen to understand what the value of that wasted food was. And we estimate that it's worth around, in total, around £100 million per year. But in terms of per person or per household, it's about £40 per month. So just to put that into context, around 15% of people living in Bristol are in the most deprived areas of the whole of the country. So looking at minimum wage in Bristol would be just under £400 a week. So just to put that into context, so it's a significant amount of money that people are throwing away. So what we were able to do is to then understand, because of that, to try and estimate these resources that are loaded into food before it even leaves the house in the bin. So, and the biggest one here is CO2, which is equivalent to about 110,000 tonnes of CO2, and 100 tonnes of PM2.5, so reducing air quality. But what this graphic shows you is how we can compare 110,000 tonnes of CO2 with 100 tonnes of PM2.5, because this graphic is using those metrics that we did to apply the unit value times the quantity of pollutant, so we can actually get a feeling for those relative scales of the importance of global warming versus particulate matter versus things like fossil resource depletions and water depletion. So the second aspect of that is then what happens when food waste is processed by waste disposal, and here we have positive and negative impacts. So we have benefits here from reductions in primary energy demand and reductions in water use, and those relate to grid energy, generation of grid electricity. So the implication is that by generating energy through anaerobic digestion and incineration, we don't have to produce lots of electricity through burning fossil fuels. But there are negative aspects as well. So in particular, increases in nitrogen, which leads to more marine eutrophication, and very strongly particulate matter from disposal of fertilizer, which is a byproduct of the anaerobic digestion in particular. So just to compare these two things, and again, this is where the economic valuation comes in very useful, is we can actually see the actual size of waste disposal here is this little square in the center, put to scale against the quantity of resources that go into food before it's even wasted. So, which then leads us on to kind of thinking about scenarios in terms of reducing food waste. What is the most efficient way of reducing food waste? So we then explored two scenarios and trying to use normal scenarios for the UK. So the first one was just saying, can we just improve recycling? So moving food out of the black bin and into the recycling caddies, which is something that our partners, Bristol Waste Company, are really keen to do, to get people to, which is this Slim My Waste, Feed My Face campaign they had in Bristol to encourage people to recycle more of their food. And the second scenario we compared with was a national campaign called Love Food, Hate Waste, which actually asks people to think more about the types of food that they buy to prevent, so that the amount of food that they buy matches how much they eat, so it never gets thrown away. So reducing it at source. So we wanted to compare these two scenarios. So and just what we're able to do here is to say 20% more recycling. If we just have a look at what happens there, so the total quantity of waste doesn't change. It just, what happens in this scenario is that it just goes into the caddies, and it goes into for anaerobic digestion rather than incineration. And so we can see there's still some positive benefits here, such as it represents about 3,888 tonnes of waste coming out of the black bins in Bristol and going into the caddies for recycling, which leads to 113 tonnes less CO2, because anaerobic digestion is a much more efficient way of producing energy than incineration. And we can see more green energy and less water use, but we also see more PM10 production and marine eutrophication. However, if we look at the second scenario, which is reducing waste at source, because what we're looking at is reducing every aspect of the food cycle, we're looking at 10,000 tonnes of less food waste, which is looking at a much more dramatic reduction. So we're looking at 15,000 tonnes less CO2, 86 tonnes less nitrogen, and less fossil resource depletion, but we're looking at 20% less green energy generation. However, that green energy generation, it's the loss of the benefits from that is outweighed by the much larger reduction in the resource burden of food. So if we just looked at...
Excuse me, can I ask you a question, please?
Yes, of course.
Okay. On the previous slide, I didn't find estimation of water percentage in the second case of 20% reduction of food production.
So in the water, oh yeah, I haven't put that on that slide. So you can see it here on this one. We have, I've separated it out for the different elements here. So we've got, in this illustration, this is just looking at
Okay.
waste disposal. But if we look at this one with waste disposal and the burden of food production compared, this is where you see the impact of those resources that are preloaded into food, as well as the impact of waste disposal across all of the different pollutants or resources. So, and I was going to touch on water actually, because it is a particular issue in the modelling. So just to put it into context, there was another study in the UK that looked at the impact of carbon and water burden and food waste in the UK. And what they did was they used a different definition of water depletion, which they referred to as water footprint. And the unit they used there was something like, it was really significantly larger than the estimation used in the Tonini study. So this is where we see some uncertainties relating to definition of water use and water footprint, which makes it very difficult to compare single units throughout the cycle. And the second study I wanted to point to was this Salim Deep study in 2017. They made the very key point that when people change their behaviours in terms of food waste, what they see is a rebound effect in terms of they change the type of product that they buy might have higher emissions and a higher environmental footprint attached to it. Things like people stop buying, for example, potatoes and vegetables and start buying different types of meat, or they might buy more packaged food, and this has a different impact environmentally. And they said that could potentially reduce those benefits by almost up to 60%. So we have to be careful about kind of overstating the benefits of some of these changes. So, and just to state, one of the key challenges here was about the comparable units and assumptions behind these databases and life cycle analyses that we've used in our modelling, and also the economic valuations themselves in terms of the unit costs of environmental impacts do have certain uncertainties attached to it. For example, if we're looking at the impact on cancer, cancer can vary in severity from relatively minor impacts to extremely serious and expensive impacts. So we have to represent those uncertainties in our models. And one key thing about this is it's a snapshot in time. So we don't model changes in carbon pricing or the effect that if the demand for recycling goes down, what that might do to gate fees and the cost of recycling. And we don't explore the changes in the food, waste, energy economies and the impact of those on household incomes, which is a piece of work that was carried out by our macroeconomic colleagues. So, but I think what it did explore for us was that it really reinforced the waste hierarchy for us to understand that prevention is most definitely has a lot more benefits than recycling, but understanding that about 30% of wasted food is not edible, and we need to make sure that this is disposed of in the most efficient way possible. And so compared to incineration or landfill, anaerobic digestion has most positive outcomes, but even here there are some things we need to be aware of. But a key part of this was understanding that benefits from energy generation rely on how much green energy can replace grid energy. And we know that the proportion of renewables in current grid energy provision in the UK is rising. And if that happens significantly, then these benefits will reduce. So that was a quick canter through my work. I'm sorry, really quick, but I'm quite happy to discuss it afterwards. But I just wanted to point to this study, which was published recently, just to summarise the work in the project. But just to say, it was a really useful exercise for us in terms of the economic valuation, and we were able to feed this information back to our stakeholders in Bristol, and that helped them with towards their goal of applying for a sustainability award for a gold standard for food, reducing food waste and being more efficient about food in the city. And yeah, so that was really helpful for us to feed that information to them. Thank you. And yeah, I guess I should ask if there's any questions.
Sure. So thanks again, Eleanor, Ali, and Yana. And please, if there's any questions to any one of these presenters, you can unmute your microphone and go ahead. Ahmed, I see your hand up. Go ahead.
I'm so glad to hear about non-market cost, but I'm asking about, are there any possibility to match this non-market cost with the loss can be happen to the farmers, or the bad effect of or without using post-harvest new techniques? Is that possible to can match these two trends together?
So what my colleagues did for the macroeconomic part of our project was to model what happens in the food economy, to see what the implication is of a reduction in consumption of food and what that might do. And that was really important for us to then look at the implication for Bristol in terms of things like food-related jobs and farming jobs locally as well, to try and consider that. And we found that, you know, that this has a significant impact on because it reduces that economy. But the one thing we did struggle with was the approaches for the bottom-up understanding of these life cycle analyses are very, very different from the kind of input-output models that are used in macroeconomic work. And that was a key research outcome, I think, for us, was to understand that the two techniques are so different that it was very difficult to bring them together into one systemic model. And I think that those kind of a kind of fusion of the two approaches would be really useful, I think.
Okay, thank you.
I want to ask how we can calculate the footprint and CO2 emission print and waste footprint. How we calculate these equations?
So in the life cycle analysis that's used by Tonini, they use a database called EcoInvent, and another database called Recipe. And those databases estimate those kind of resources and environmental footprints in terms of many different endpoints. So it's really useful. And what those life cycle analyses then do is just then combine all of those different inputs at different stages in the cycle. So I'd suggest maybe having a look at those first to see the modeling, because it is, I guess it would be highly specific to the geographical location that you're exploring.
Yeah, I was going to say that it's most likely that these values differ from country to country and place to place based on, you know, the way people do agriculture, the way that they distribute, the practices of consumption, recycling, and so on. So if there is a resource to see that is location specific, that would be very useful. Any other questions? If not, I have a quick question that is kind of very general, and I don't expect there's a yes, no clear answer there. But if any of the three of you, Yana, Eleanor, and Ali, had to suggest a way to remediate or reduce this waste in our food processing consumption and increase the benefits, where would you put the emphasis on? Changing management, policy, behavior, individual human behavior, education? Where do you think would be the most effective solution?
Shall I go first? we had a quite big discussion about this, because I think my work focused on households, it very much feels like it's households' fault, and actually that wasn't the intention, because I think one of the key things that we talked about was very much that households are only part of this system of food production and food consumption. And actually maybe what we need to look at is actually the choice architecture in which decisions are made about food, and about how people then produce food and how people waste food. Because I don't think anybody goes out with their shopping basket to say, well, about, I'm going to waste some of this food. But it's just the way that people buy food, perhaps in the UK, helps to drive that, and how we shop, and the options that are offered to us. For example, if we bought much more sort of long life food, maybe less of it would be wasted, but then that would have implications then in terms of different footprints. So yeah, there was a big promotion in the UK about how supermarkets sell food. So for example, there was a big thing about, because there was a 2-for-1 deals on salads and things like that, fresh salads, so people were overbuying them and then just wasting them. So perhaps it's about what choices people are given as well. I don't know if the others have stuff.
What do you think, Ali? And can you maybe compare it to like behavior policy in Afghanistan, where you're coming from?
Actually, first, my modeling doesn't actually answer this question. There's a different approach in that modeling, and I don't look at the specific causes of the food waste generation and the behavior of the people. But obviously, I think the behavior change could be is the key, and because the majority or most of the food arises from the households, we should look at the households very closely, and we should find out the ways which can incentivize people to reduce their food waste, which is a very challenging, tough job. So because as far as I know, even I found out during my interviews that even it's very difficult to convince the people by telling them the amount of how much money they're gonna save if they reduce food waste. I mean, it's very difficult, complex challenge question. In terms of Afghanistan, I think that if I want to like model the food waste in Afghanistan, I would say it would be a very different model, because the food dynamics and food waste dynamics are much more different in Afghanistan. So in Afghanistan, we do not have the AD plants, incineration plants, and as well as the food waste generation in specifically in the households, and even at hospitality sector and other sectors is much lower than the UK because of the economic and the cultural context of the society.
Thanks, Ali. And Yana?
Yeah, so I think this is where really also social science plays a big role in understanding these dynamics and the causes and what you can actually do about it. And so what I presented around stakeholder analysis is just one aspect. I also have a PhD student currently working in Port Harcourt in Nigeria on food waste, and that's probably maybe a slightly more similar setting in terms of what's going on specifically around food waste, maybe compared to Cairo and Egypt, etc. And what we are looking at there is actually the retail sector and how it's this interface between what is defined as food loss around the food production, the agricultural sector and transport, and then you have the retail sector, which plays such a big role also in food waste production in the UK at least, and where there's relatively little known in the Nigerian context. The issue is there that we actually have an increase in the factors like supermarkets, increase in middle class, etc., which has led to an increase in food waste in countries like the UK. But this is happening now in Nigeria as well. And so she has studied quite a lot of the processes going on in these sites. And it's certainly not just households who are producing food waste, it's also at this retail interface. And this is both that within the stores themselves, food waste is being produced, but also, as Eleanor also indicated, there are certain incentives in how you purchase food for households, which then makes it harder to avoid food waste. And so I think there is a complexity around food waste specifically. But to bring this back to the nexus, I do think that similar behavioral challenges are around energy and water, especially when they are perceived as a basic good, and certainly until recently, and all of these things are changing, water and energy was somewhat affordable, but we have challenges now with the international political situation, etc. But I do find it's really helpful to engage with social science methods on this as well, to understand how can we actually change behavior, but also change systems which enable and hinder certain behaviors.
Cool. If there's no more questions, let's thank Yana, Eleanor, and Ali again. And I think there's a 10 minutes break, and then we go to our second talk for today. So I would personally like to thank the speakers, and I'm sure everybody enjoyed their presentations, and I will share their contact information in case somebody wants to follow up with specific questions to them.
Thank you.
Thank you, everyone. Bye and good
Thank you
luck.
so much.
Thank you.
Bye.
Hi, Ronnie.
Well, you're here. Morning, Adina.
Yeah, it's morning for us. I think there's now some break until 9:45 our time, and then people will join again. I guess it's
okay.
Short break. I don't see that Kevin has connected yet. I assume he will.
I will ping him just to make sure. Okay.
Perfect. And you have screen sharing access and everything.
Okay, great.
Perfect.
Okay.
So I'll go make myself another cup of coffee. Hi, Kevin.
Hello, pleasure to see you.
Can I go ahead and put my presentation
Share the
up?
screen? Yeah, you can share the screen now. If that's
Okay. Oops.
perfect. Looks good.
Get rid of that. I think at the bottom.
Is there still a field trip planned for the 12th, Ronnie?
Yeah, we're having the next workshop is on the 12th, and we're having a site visit by someone from the funding agency. So there's going to be some sort of tour for that person, if you know, and I don't know if probably after lunch. I'm just not sure about the scheduling for that.
And
But that's
Adina, we can arrange, I'm happy to personally show you around, or we can arrange a tour pretty much any time that's available. We just need to let them know that we're coming.
Yeah, no, I'll do my best to join you on the 12th. I put it on my calendar. Once I know where and when to meet, I'll do that. If that's easier.
Adina, can you see the control panel on the screen?
No, I see it presenter mode. It's good.
Okay, because I have this, little thing at the top there.
Yeah, I think when you're presenting, you can only see, the presenter,
Okay, here we go. All
But
right.
no, it looks fine.
Okay.
I think we'll just wait another few minutes and
Yeah.
then.
So Adina, we did not end up combining our presentations. So when there are questions, each of us will just have to jump in with.
Yeah,
our
that's
plan.
not a problem. It
Okay.
worked fine for the previous session. Each
Okay.
one had their own PowerPoint and used that.
All right.
Right. What is hello in Arabic? Is it ahlan?
Ahlan could be fine, or salam alaikum.
Well, I always thought it was, now I forget how, never mind. Okay.
I think we can start, Doctor. It's nearly the time. You are muted, Dr.
Oh,
Edith.
sorry, I'll go ahead and get started then. Thank you, Rana.
Thank you.
So welcome back, everybody. The second session for today will take us to a different continent and a different case study. And this time we will focus on the socioeconomic aspects of small farms and their relation to the water energy fuel mixes. The speakers for this lesson will be Dr. Ronnie Lipchitz and Dr. Kevin Bell. These are close colleagues of mine from UC Santa Cruz. They were the leaders of developing an academic program at the university called Sustainability Studies. However, in this presentation, they'll be talking about a project that they initiated as part of the SSRF, which is the Sustainable System Research Foundation, a nonprofit green think tank that they have started. And Ronnie will tell us more about this organization, and both speakers will share examples from their work in local farms in California. And with that, I'll let Ronnie talk more about SSRF and that project.
Everybody. It's a real privilege to be able to do this presentation. I wanted to start out with a couple of observations. First of all, my presentation at least, and I think my colleagues Kevin Bell's presentations will be somewhat different probably than what you've been hearing. I'm not going to talk much about technological systems or the kinds of things, for instance, that were addressed in the previous presentation. I'm going to focus more on the sociology of small farms and their operators. As a way of background, I retired a couple of years ago from UC Santa Cruz after teaching international politics for 30 years. I have a PhD in something called energy and resources from UC Berkeley. But so over the years, I've done a lot of work in energy and resources and technology policy, and also trying to understand the behavior of people, of individuals, with respect to these kinds of systems. It's very easy to think that everybody approaches these sorts of issues rationally, and if they see the benefits of adopting a new technological approach, they will change very easily and quickly. I hope, by the way, that I'm not telling you things that you don't already know. But in fact, if we observe various kinds of development projects, technology transfer, what we actually see is that it's much more difficult to accomplish these kinds of goals than one would think of in a kind of a friction-free research and policy environment. There's a lot of friction in moving from the theory to the practice. So before I tell you about SSRF, I want to just say a couple of things about successful technology transfer. At least this is sort of how I think about it after 30 or 40 years of trying to think about it. That if you go into any particular place, and we're going to be focusing on small farms, particularly here in California, it's critically important to think like a sociologist and an anthropologist. You need to build relationships of trust that respect local social structures. You can't just sort of go in and say, here, I'm from the university and I'm here to help you. You have to consider language and literacy in explaining and training. That's a problem that we encounter here in California. You do need to understand customary practices and how people, farmers in this case, might be resistant to change. You need to be aware of structural barriers, for example, lack of access to capital, to agricultural loans and things like that, that may impede adoption of technology or practices. And I think the last one is that technology ought to be easy to repair if that becomes necessary, and not dependent on ordering replacement parts from far away. So those are sort of basic observations. Now, the Sustainable Systems Research Foundation is a nonprofit green think tank and project incubator in Santa Cruz, California. And I'll let you read the blurb there, but Kevin Bell and I were two of the co-founders, and we started this because we were frustrated with the environment in the academy, which is largely focused on theory and policy and rarely focused on going from that to action. And we were interested in developing projects locally that could be replicated elsewhere and scaled up. And so we're doing work on solar microgrids. We're doing work on waste management. And one of the projects that we are pursuing is what we call the Sustainable Urban Food Initiative. And that is essentially about trying to help small farmers in the area adopt agricultural technologies that are suitable for small farms. So the project that we're engaged in now is with an operation called Whiskey Hill Farms, and we're providing a series of agricultural technology workshops for small farmers. Now, here's another sociological observation. We initially designed these for farmers who were experienced with the US agricultural system, and we adopted a methodology which is essentially to stand in front of the room full of people and lecture to them using PowerPoint. As it turned out, the farmers that we expected to sign up did not sign up, but instead we got about 10 Latino farmers and farms to attend the workshop. And I'll say more about Latino farmers later. They're primarily people who over the time have immigrated into the United States and worked as farm workers. So we had to pivot and restructure the workshops to meet their needs, experience, and situations. So our focus is on the 3 counties in California in the box below: Santa Cruz, San Benito, and Monterey. We're very kind of narrow in that respect. You can see that the agricultural areas in California are much, much wider, much broader. In the Central Valley, which is this area right here, there was a lot of large scale farms with lots of Latino farm workers. But these larger farms are much more technologically advanced than the smaller, in the sense of using, equipment, expensive equipment, and various other kinds of techniques. Small farmers are not quite in that position. And most of the farms in this area, or many of the farms, are relatively small. Whiskey Hill Farm is a 14-acre organic farm near a city called Watsonville. And it's a pioneer in adopting a systems approach to agricultural technology. It recycles and reuses various inputs and outputs and demonstrates the design and best practices of a circular closed-loop food economy. Kevin's going to talk more about this when he does his presentation. But in essence, they try to use to start with crop residues and organic wastes as a source for making alcohol, and then using the byproducts from that process to grow crops and to make them grow better. And this is a diagram of what they do. Since I think this is being recorded and you can get a copy of our presentations, I'm not going to say more about this for now. So let me talk a little bit about small farms. According to the recent research, there are more than 600 million farms in the world. 90% are family farms and they occupy 70 to 80% of arable land and produce 80% of the world's food in value terms. Small farms of less than 2 hectares, however, account for 84% of all farms worldwide, but they operate only about 12% of all agricultural land and produce roughly 35% of the world's food. But that means that there are more than 500 million small farms in the world that support roughly 2 billion people. So that's a pretty significant number, even though they're not producing the majority of the food. There's no data about how much of the food produced by these small farms is sold in markets. One infers that a lot of these farms are basically subsistence farming. And many of these farmers cannot afford to eat the food they grow, and they rely on low-cost foodstuffs to survive, to feed their families. That's true with the farms that we're working with. Many small farms lack capital to invest in raising productivity or bringing in technology. Many small farmers rely on family members and networks for labor and support in hard times. And the social structure of small farming in rural communities is very different from large industrialized farms. Now, the structure of the US agricultural system is in many ways, I won't say it's unique to the United States, but it sets up a particular set of barriers and obstacles to small farmers. The system is dominated by an agro-industrial complex that favors large technology-intensive farms with large capital and resource endowments, but low labor requirements. The number of farmers in the United States has declined drastically since the beginning of the 20th century because of consolidation and because of technology. And there has been constant migration from farms in rural areas to cities. This is true across the world. As farms become more technology intensive, labor requirements drop, and the people who are thrown out of work migrate to cities. And it's also true of younger generations. They may decide that they want to go into some other field as well. So farms in the United States are growing larger due to purchase and consolidation of smaller family farms. Those farms may be pretty large. They may be 500 hectares or larger, but they're considered small by the standards of the large agro-industrial farms. So the number of farmers in the United States is declining, although interest in farming paradoxically is growing. The agricultural education and research system is science-based, and it's directed toward identifying interventions that can increase productivity of high volume crops. Science is a very important factor in determining what sorts of innovations and improvements will be pursued by this agro-industrial complex. It's also assumed that new farmers will receive a college education prior to their entry into the sector, so that they will be familiar with and prepared for dealing with the bureaucracy, with floating loans, adopting technology, and things like that. That's not always the case. And the system is highly bureaucratized. And I'm sure, what I know of Egypt, that you face the same kind of highly bureaucratized setting. Small farms we define as less than 50 acres or 20 hectares. The USDA's 2017 agricultural census has reported a decline in small farms, even as the number of new producers was increasing. 47% of the nation's 2 million farms were less than 49 acres in size, and almost 3/4 were less than 200 acres, or about 100 hectares. And of those, 86, well, I don't quite know what I meant here, but many of those, let me put it this, many of those, 78% brought in less than $25,000 in annual sales. So many family-owned farms supplement their incomes by non-farm employment. And this doesn't mean that the farm is a hobby. It just simply means that they cannot earn enough profit to support themselves and their families. And this is increasingly apparently the case with small farms. Our focus, as I said, is on Latino Hispanic farmers in the United States. These are people who have emigrated to the United States over the last 30 or 40 years. They came to the United States to work as farm workers. They're dramatically underrepresented among US farmers, as you can see, 18.5% of the US population, more than that in the West and Southwest, but only 3.3% of US farm producers. Of the country's 2.7 million principal farm producers, about 400 to 800,000 identify as Hispanic, Latino, or Spanish. In California, I'll just call them Latinos, okay? They're 40% of the population. They comprise 11% of the farms. They farm 16% of the land. And you can see, I have some numbers here, 14,600 Hispanic, Latino, and Spanish origin producers in California. Again, a small fraction. There are also between 400 and 800,000 farm workers in California, most of them from Mexico and Point South, and many lack documentation. That is to say, they're not here under legal terms. And I want to make one thing clear, that these numbers are sort of squishy, okay? They're estimates. when censuses are done, many of the people who are undocumented don't want to participate. They don't want to be counted. They're concerned or afraid that they might be pursued by the immigration authorities and deported. And so we don't really know precisely the number of farm workers and Latino farmers in California or in the United States for that matter. I want to show you then a video here of a short video about the first Latina farm worker turned farm owner in California. And this is a video courtesy of an organization called Farmers Footprint.
Cuando estás en México, escuchas que Estados Unidos es el país de las oportunidades, pero cuando yo llegué a este país y trabajaba en el sol, en el aire, en la lluvia, en el calor, yo pensaba que sí era un país de las oportunidades donde estaba la mía. Mi nombre es María Inés Catalán Rebolledo. Soy un pequeño agricultor en Hollister, California. Emigré a California hace más de 30 años, siendo madre soltera con 4 hijos. Y llegué a trabajar a los campos. Yo me preguntaba qué tipo de agricultura era agricultura orgánica. Me di cuenta que era la misma agricultura que mis antepasados, mis abuelos, mis padres habían estado haciendo en México. Yo pensé que si algún día yo llegaba a tener nietos, yo quería que mis nietos tuvieran mucha comida y fueran libres, como fui libre corriendo en los campos con mis abuelos. Empecé a trabajar y a soñar y a prepararme para ser un pequeño agricultor orgánico. Tuve que aprender a manejar tractores, equipo pesado como mujer. Tuve muchos retos, muchas barreras, porque estaba entrando en una área que era solo para hombres que hablaban inglés y personas que tenían dinero para invertir en la agricultura, para pagar la renta del acre que me dieron el primer año. Yo lo pagué lavando los baños de la oficina, limpiando las oficinas de Rural Development. Yo empecé mi negocio sin un centavo, ni un penny. Tenía dinero para invertir en mi negocio. Culturalmente, la mujer nunca fue cabeza o líder de un negocio en la agricultura. Es muy difícil que te acepten también en los negocios, jamás. Lo logré, ahora tengo mis nietos que todos han crecido, gateado y caminado en el lodo, en la tierra, tienen mucha comida. He logrado el sueño que tuve de que mis nietos fueran libres y mis hijos fueron libres.
Okay, so as I said, many of the Latino farmers in California, or at least in the region that we're working in, like Maria Cardenas, were formerly farm workers. Some of them have gone to a regional agricultural training school called ALBA to learn how to farm and to run their own farm. Virtually none have college degrees, and many speak only Spanish, or some don't even speak Spanish. They speak an indigenous language, and they come to rely on their children to translate materials and do anything that has to be done online. Most of them farm small leased parcels. They have limited capital. They cannot get crop loans because they don't have experience or they're undocumented, sufficient experience or they're undocumented. They're market takers, that is to say, they have to accept prices for their produce that are being offered, and they rely on family members for labor. So a lot of what you would call social capital. These are just some numbers. Again, you can see that about the 3-county region. What you can see from this is that the average farm size in the 3 counties is large. Santa Cruz County is actually has the most, it's the smallest farms, okay? But the number of farms of less than 50 acres is close to half. The average market value of products sold per farm is this number right here. But a large number of these farms have sales of less than $10,000 a year. So it more or less mimics the national picture, which is to say, agriculture is dominated by large farms, but there are a fair number of small farms that are found there. And they're not irrelevant. They're important to food provision, in close into urban areas. Well, how have these farmers learned to farm? Well, a lot of them have learned the craft in Mexico, where they grew staple crops such as corn to sell, and then food crops for their own consumption. They acquired their knowledge from extended family networks and by working with experienced family members. They come to this country, many of them come to this country already knowing how to farm. What they don't know, of course, is how to farm in the United States. In Mexico, their farms relied on hand labor, and technical innovation was largely too costly to deploy. Their exposure to markets and capital accumulation was limited. They didn't have to buy seeds every year. They traditionally worked on ejidos or village communal land. These were privatized, and Mexico allowed cheap corn imports from the United States into Mexico, which then became a significant push factor in migration to the US farm sector, because farmers couldn't sell their, were competing with much cheaper American corn, basically for the tortilla market. Tortillas are very, they're sort of like pita, although thinner, much thinner, made of corn. Okay, so they face a lot of obstacles. And some of these is already repetitive. Land is very expensive, so mostly small acreage from family and friends, or Anglo farmers will live with available land. They rely on pumped groundwater and buy water from larger farms, and increasingly water supplies are limited due to drought. Capital is limited. Virtually all income goes back into operating the farm. Many are not eligible for state and federal support because they're undocumented, or they don't have, as I said, farming experience. They don't eat the produce they grow and sell, and they rely on much cheaper beans and rice for food. And then they sell their produce to certain distributors who tend to impose high costs, delay in paying them for sales, and may tell them that nothing sold for whatever reason. So you can see what I've done here is made a diagram of the bureaucratic environment, the economic environment, the social environment, and the resource environment. These are obstacles faced by Latino small farmers in California. These are obstacles faced by all farmers, but larger farmers and Anglo farmers, American farmers, have much more experience in dealing with some of these things. They have much more in the way of social capital, connections, networks. And this, of course, is what happens when you come to a new country and you have to learn the rules by which, various kinds of sectors operate. So if you're going to go and try and do technology transfer to a small farm, and these are things that we are just gradually learning, although in many ways they're kind of intuitive, you've got to look at the following factors. Social relations and social reproduction, that is to say, what is the family and relational structure? Who has power? Who controls resources? What sort of food production frameworks are there? Are they producing for cash crops, for export, for subsistence? If you want them to become more productive, what does that mean in terms of what they might give up? Social practices, well, that's included already. Resource access, local knowledge versus science and technical knowledge. Farmers in rural areas, even if they're farming small areas of land, or they're immigrants, they have a certain amount of knowledge and experience in working with the parcels that they own or that they farm. And that shouldn't be downplayed, because that can be very important in terms of thinking about how do you help them increase productivity or encourage them to adopt technology. Again, customs and history. If I were to do this again, I would edit this list down. What are the costs of change, the opportunity costs of change? That's always an important thing to remember. So if you want to do this, do technology transfer, it's really important to go in and do some field work into the place that you're trying to transfer the technology to. And I'm not going to, because of time, I'm not going to say very much about this. Again, this is about the social relations of production, and it replicates what I just was saying to you. So I'll leave it for the moment because I want to give Kevin time to talk. So Shukran, thank you for listening. And if you have any kind of questions about this, you can write to us at this email address or look at our website, sustainablesystemsfoundation.org. And we encourage you to contact us. Thank you very much. Let's see, I have to now figure out how to, okay.
I think you just press stop sharing. It's like, Aya, you have the questions?
Yeah, I have a question, please.
Go ahead.
Okay. We have this case in Egypt, the same case, but not for the immigrant farmers.
Right.
We have the same problems,
Right.
but in the less amount or the less number of acres, smallholders here in Egypt have about less than 3 acres per farmer.
Right.
So are there any suggestions to get our farmers benefit from this system?
Well,
And yeah, go
let
ahead.
Kevin go ahead and answer that. Yeah.
So one of the features of the farmers that we're working with, and many of the organic farmers in the Monterey Bay area, and one thing you need to understand is that because it's close to San Francisco and Silicon Valley, there is a market for organic food, and there's a lot of interest in kind of direct channels, farmers markets, direct connections to stores and restaurants. So it's a slightly different situation, but the farms that we're working with are in the range of 1 to maybe 15 acres. So they're not out of range of the farms that we're talking.
Kevin, you're muted.
Excuse
Sorry.
me, you're muted.
So a lot of the farmers that we're working with are on farms that are 1 to 15 hectares. They're in the range of a lot of the farms that are in Egypt. And a lot of the technologies that I'm going to be talking about reflect that. We're trying to focus on technologies that are useful to farmers, that are, some of which is in the range of a typical farm in Egypt.
Yeah, thank you so much.
Thanks, Ronnie. You can go ahead and share your screen. Not Ronnie, sorry, Kevin. You can go ahead and share your screen so you can then have more questions if there is more questions after your presentation.
Okay. 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 So
There.
okay. So
Kevin,
yes.
You're not in presenter mode. If you go to your first slide again, and on the lower right side, there's this little symbol for your computer.
If you can, I have 2 monitors. I am in presenter mode on my side.
So we see your presenter mode.
I am in, can you see the slides?
We see the non-presenter mode. We see your notes.
That's fine. Oh, you're seeing the other one.
Yeah.
Okay. Interesting. All right, hang on.
If you keep that and go to the bottom right side,
Mhm.
yeah, there's the little computer, no, there, little left. There's the little, yeah, that
I saw
thing. Yeah, yeah.
There we go. Okay, is that working? I'm sorry, on my monitor, it looks fine, but so you're seeing the presenter side?
No, we're seeing your notes again.
Dang, okay. Hang on. Okay, is that working? You're still seeing presenter side?
We're still seeing your notes, yeah.
Darn, okay. All right. This is not happening on my side. I am so sorry.
Kevin, I think if
Yeah.
you go back to the end slideshow and you go to view,
Okay.
just try that, because for some reason your notes are showing up.
Yeah, I'm not sure why that's
Click
happening.
view. Oh, here, will you see, click on, it says notes there.
Yes.
You click on that and see if you can turn that off.
Okay, there we go.
There we go. Maybe that'll work.
Okay, let's try that. Is that working? Is that working now without the notes?
Nope.
Oh, okay, let me try one more thing.
It's probably not worth the time to
Yeah, I
actually, yeah.
Is that, and you're still getting the notes?
Yeah.
Oh, okay. Let me disconnect this other monitor. I'm sorry about you guys.
What about the display setting? There, next to the end show, there's a display setting. Maybe that's where you need to change something.
I'm sorry. Oh, and on Zoom?
No, on your screen, there's a, if you go left, there's something that says display settings.
If you want to let me do the slide, I can do it without the notes, and then Kevin can just tell me to change.
No,
slide.
that's okay. I'll tell you what, I will disconnect my other monitor and I will do this without notes. So.
Yeah, but the notes are still
Is that working
showing.
now? No.
Yes,
it's
now
good,
it works.
yeah.
Yes.
Okay.
now, okay.
Okay. So the problem was my other monitor was, it was supposed to just pick up the monitor that has Zoom on it, but it was picking up the other one. So, so I don't have my notes. I think I know what I'm going to say. I wanted to start quickly with this chart that Ronnie showed. I'm not going to spend any time on it, but it's really important for understanding the context for the farms that we're talking about and the situation that they face. I wanted to talk a little bit about Maria Cardenas. She's one of the farms that is participating in our workshops. And the point that I wanted to emphasize from what Ronnie was talking about is that she is an excellent farmer. She grows very high quality produce. Because she is a native Spanish and indigenous language speaker, she has no connection to the market infrastructure and the social infrastructure in the United States. State or nationally, Latinos are about 18% of the population. In California, they're about 40% of the population. In rural areas, in rural agricultural areas, they are a majority of the population. And so it's a population that is really separate from the Anglo population of California. I wanted to talk a little bit more about the area that we're looking at. This is about 2 hours south of San Francisco. And the the little yellow peninsula that you see there is the Salinas River, which provides most of the water to the area. Central Valley, California has very large dams and water projects, not dissimilar to projects on the Nile. This part of California relies entirely on rainfall and groundwater. Typical rainfall is about 1 meter a year. It's actually not bad, but the range is from maybe 30 centimeters to 140 centimeters. And because we've had a persistent drought in the West for the last decade, it's tended towards the low end of that. And I want to talk a little bit about water because I think it's one of some of the issues that small farmers face, I think, are roughly comparable to some of the things that are some of the patterns, larger patterns that happen in Mexico. So one of the things you need to understand in the United States is that in the Western United States, the way that water is allocated is whoever got access to the surface, to the rivers first, always has primary access to that water, senior access to that water. Anybody who comes later has to get in line behind them. And so if you are a new farmer with junior water rights in a dry year, you get nothing. Because the water is over allocated, in a normal year, you'll get nothing. And so for most of the new farmers and for the leased land that's available to them, there is no surface water resource. The Salinas River used to be a significant river size, used to be fairly large. It no longer reaches the ocean. It is completely over allocated. Surface water resources are not available to these farmers. This is a profile map of the aquifers in the area that we're talking about. There's basically a shallow aquifer that's fed by rainwater. It's been pretty much pumped dry. There are 2 deeper aquifers that are being pumped out, being overdrawn now. A lot of the leased land that's available to these farmers is into the shallower of those 2 aquifers, and the larger farms in the area have tapped into the deeper aquifers. So those farmers that we're talking about are facing some serious constraints around access to groundwater as well. The other thing that's happening is that because we have overpumping of groundwater, less surface water reaching the ocean, and sea level rise, we're starting to see saltwater intrusion into some parts of the area. And this basically shows the expansion of groundwater into some of the richest agricultural land in the United States. So the bottom line is that for a lot of these farmers, access to water is one of the critical issues that they face. And from here, what I'm going to talk about is we're going to look in a little more detail at Whiskey Hill Farms, which is essentially a research laboratory. It's not necessarily a model for what farms should do, but it demonstrates a lot of the core principles of circular economy for agriculture and of regenerative agriculture. And then from there, I'm going to talk about maybe a handful of some of the technologies that we're talking to farmers about and why we think they're appropriate. So, what's happened? Okay, one of the other issues, of course, is that this area has been farmed for a very long time, and it's been industrially farmed for the last 50 years or so. That means that a lot of the topsoil has been stripped away and a lot of the nutrients have been stripped away. What we're trying to move back towards, in essence, is a cycle where agricultural production is keeping up with work that we're doing to rebuild soils and put nutrients into the soil and build a base of land that can sustain a lot of food for a long time. And this is just I won't spend a lot of time on this, but these are some of the kind of underlying principles of regenerative farming. They're applicable everywhere in the world. And again, the idea here is to restore lands that have been that have lost soil, and to in the process, you are increasing the water retention capacity of that soil. You are increasing crop production. You have healthier crops, And significantly in the context of climate change, you are sequestering a significant amount of carbon. Restoration of soils and wetlands and forests can be a significant part of basically reducing the amount of carbon that's in the atmosphere. Okay, so start with Whiskey Hill Farms. This is a 14-acre, I'm sorry, about 11 hectare, no, about 7 hectare farm that's located in South Santa Cruz County. It was formerly a premium flower farm, and it was driven out of business in the early 2000s by cheap imports of flowers that were flown in from large farms in South America. At the time that this was taken over, the topsoil had been stripped away completely. It was down to mineral subsoil. Since this farm was bought by Whiskey Hill Farms in 2007, it has restored about 80 centimeters of soil, of topsoil. I'm going to spend a little bit of time on this, just walking through this process. So from basically the feedstock for producing ethanol is crop waste and food waste. It produces alcohol. It has a couple of, some of the intellectual property is some low energy techniques for refining alcohol. So the net energy balance is very high compared to alcohol production that uses corn, for example, as a feedstock. So besides alcohol, you're getting carbon dioxide. That carbon dioxide is captured. It's run through drip lines to provide carbon dioxide at the level of the plants so that it enhances plant growth. Or some of it is compressed and used commercially for beer, soda pop, industrial applications for carbon dioxide. There is a liquid and solid residue that is composted to produce methane. That methane is captured. And in this context, it's used to heat water, to heat the greenhouses. This is a mix of greenhouses and fields. The solids, or the liquids, now you have liquids that have a lot of nutrients in them that needs to be purified. They run through pools that have bulrushes. It's a type of reed that produces high quality of protein and fiber. That is harvested to produce protein, and it doesn't show it on here, but the fiber is used for manufacturing. And then from there, it basically meets California Clean Water Standards and can be reused as a water source, or it can be instead of cleaning up all the way, you can divert it into a pond that provides nutrients for aquaculture. The solids go to a compost pile. The compost pile has pipes underneath to capture heat from the composting process, which again is used to heat the greenhouses. It also runs air through drip lines, so you don't need to turn the pile. So it's an aerated pile that can just sit there until it's fully composted. And that compost, again, is used on the farm. So everything gets used, everything gets reused. The feedstock is basically produces a range of products, including food. And this just quickly goes into I'm going to start talking about sensors and controls now. So these are just examples of some of the things that you want to know about when you're trying to maximize crop production. And using sensors and controls for agriculture it's a big topic right now, but a lot of the context for it is for industrial farming and large farms. And so you see diagrams like this that are very complicated, very expensive, and integrated into systems that are not only used for agriculture, but for military applications, for surveillance applications, for infrastructure monitoring. And most importantly, it's an infrastructure that is not in the control of the farmers. And the farmers are customers. They are not participants in the process of using those sensors. This level of sensors and controls is completely out of reach of small farmers. So here's an example of an alternative. This is a sensor and control cluster that was developed by some of our electrical engineering students at UC Santa Cruz. It's currently in beta testing and field testing. We're going to be giving these sensors to the farmers in our workshops and following them in field tests to improve and refine and evaluate the usefulness of this technology. And it's fairly well thought out as far as the design. This is an early unit. What you'll see here on the left is a spike. That spike has soil moisture sensors at 15 centimeter intervals. Because this is modular, you can affect our default configuration is about 45 centimeters long, which reaches the root zone of most annuals. Technically, you could make it as deep as you want. You just keep adding units. The diameter is the same size as a standard coring tool for soil testing. So you basically use a core sampler, drop it in, you're done. Configuration takes about 10 minutes. I won't spend a lot of time on this, but basically there's the current set of sensors is, there's a couple of other things here. It also includes humidity, moisture, temperature. It also includes solar radiation. And I guess lights on here. It also has 6 separate channels for adding custom sensors for whatever applications you want to apply. It can use any standard communications protocol. If you don't have cellular or Wi-Fi, you can use low-level radio frequency. You can use cheap cellular access. There's not a lot of data, so costs are very low. If you have access to Wi-Fi, which a lot of these farms do not, you can connect it directly into the internet. And it can integrate with other sensors and controls that you're using at the same time. I'll be talking about aerial sensors along with that. In addition to collecting the real-time data, you can look at historical climate data and weather forecasts. And over time, it starts to optimize the control part of this for the microclimate that it is operating in. So the longer it's there, the better it's getting at anticipating the proper moisture levels for whatever crops and whatever stage of crops you're growing. You can set up multiple user interface options. You can use them in any language, and the control part of this is that you set the parameters, or you automate the parameters for determining when you need to run water. When it needs water, it turns a solenoid valve, water goes on. When there's enough water, it turns off. Globally, how much water you save by doing this depends on climate, what you're growing, what the soils are like. It ranges between about 10% savings and about 60% savings. In our part of the world, it's about 30–35% savings. And it also increases productivity because you're not overwatering or underwatering. And you can see, again, the range is usually between about 10% improvement in yield and 50% improvement in yield. This is an example of the beta interface. I can actually do a live demonstration of this if you'd like in questions, but I'll move on. But the point is, this is a fairly simple interface. It can be localized. You can drill down into information that's as detailed as you want, or this interface was designed for home gardens, so it's fairly simple. There's a lot, in addition to ground sensors, there's a lot of excitement around aerial sensors, mostly using unmanned aerial vehicles and satellites. What that allows you to do is, instead, the soil sensors are looking at, or the ground sensors are looking at a specific point in the field. If you have a lot of money, let me back up here. The production price for this unit is about €60. So it's well within range of a small farmer, with paybacks that you can see in a couple seasons. So this is an example of a technology that's appropriate for very small farms. So you can, there's a variety of things that you can look at from an aerial perspective on a farm level. And when you integrate that with ground sensor data, you get a very precise, very detailed, real-term understanding in the ground, in the plants, in the environment the plants are operating in, under stresses like water stress, disease stress, insect stress, of what's happening in every part of your field, so that you can basically, your farm operations are tuned to what the field needs, when it needs it. Again, improvements in productivity and increases in efficiency are dramatic down to the scale of a very small farm. The problem with a lot of the aerial monitoring is that it depends on equipment like drones. The sensors tend to be fairly complicated and expensive. They're very difficult to maintain, typically by small farmers. A lot of them use proprietary parts. The alternative, fortunately, is we have a lot of, you can assemble sensors from open source plans using off-the-shelf parts. Those parts are very cheap. You can produce sensor clusters locally. That is not on a farm scale, or you can if you want, but basically there are things that you can do on a local or regional scale that will work and that will work well and that are easy to maintain and replace. If you, in the United States, one of the options for aerial vehicles is you could have a group of farmers get together and have periodic overflights. In other parts of the world, or for small farmers here, that's not an option because it's too expensive and too complicated and they don't have control of it. But one of the things that's been done in other parts of the world is you basically assemble a cheap instrument cluster, or you attach a smartphone and you use a balloon and basically just walk around or bicycle around and basically collect data, collect data that way. What's happening with this approach is that you are getting 90% of the benefit of ground and aerial sensors at maybe 5 to 10% of the cost, which brings it into the range of affordability and maintainability and access that's appropriate for small farmers that are facing some of the issues that our farmers are facing. This is one of the greenhouse. I'm going to move now and briefly go through some other technologies. This is one of the greenhouses. Again, Whiskey Hill Farms is a field complex and a greenhouse complex for some of their demonstration projects. What you see down here is one of the reed beds that purifies water and produces protein and alcohol. This is an example of one of their aquaponics ponds, but I want to focus on this pink area up here. These are solar collectors. Again, they were developed by a research team at UC Santa Cruz. And what they do is collect solar radiation, cut out the parts of the solar spectrum that are not used by plants for photosynthesis, and UV light and infrared light, which is basically heat, so it reduces overheating, and takes that energy and directs it to photovoltaic collectors. So on the inside of these panels, they're basically transparent or translucent. On the inside of these panels, you're getting 75% of the solar spectrum, and you're getting the part of the solar spectrum that is most conducive to plant growth with reduced heat and UV radiation. So there's an enhancement of production and reduction of overheating. This is just a diagram of how this works. You see a wide spectrum of solar radiation coming in. It's bouncing around inside this special dyed surface and is directed by waveguides to photovoltaic production. The efficiency of these is not great. A high-end solar panel can reach about 20% efficiency, collects about 20% of the sunlight that falls on it. This collects maybe 4%. But for low voltage, low power applications, fans, pumps, in remote areas that don't have electricity, lights, refrigeration, it works very well. At the same time that it's enhancing plant growth. You can set it outdoors if you want to. Basically, in high sunlight conditions, photosynthetic activity tends to be reduced. This extends the amount of time during the day that you have plant photosynthesis, and reduces overheating. Therefore, you have less evapotranspiration. Therefore, you have more efficient water use and the plants aren't as stressed. This is fairly cheap. It's robust. And it's simple. Once it's installed, it just sits there and works. Lastly, I want to talk about a tractor that we've been demonstrating with these farmers. This is called the Ogun tractor. It's based on a legendary American tractor design from about 1950 that has been used all over the world because of its reliability and maintainability. This is an updated version. It's built entirely out of off-the-shelf parts or welded or machined components that you can build out of standard stock found in any machine shop in the world, with equipment, welding equipment and metal machining equipment that's common pretty much everywhere. It's basically an open source design. You can assemble it yourself. A country or a region could decide to start assembling these. One of the better versions of this is being manufactured in Cuba. It is overkill for a 1 hectare farm. It's appropriate for a farm that's in the range of 5 to maybe 100 hectares. Or if you have a small co-op or a village co-op or some kind of commons, you can, it's affordable. The Cuban version of this is about 9,000 euro. The US version is about twice that. You can drop in any of it. There's about a dozen kind of standard engine configurations that are widely available that you can drop into it. You can use pretty much any fuel that's available. The attachments and fittings are all standard size, so it'll take a wide variety of attachments that you can purchase or, again, that you can assemble yourself. The point of this is that there's been a revolution in technologies that scale well to small farm applications where the farmers are facing a lot of the challenges that Ronnie talked about. There is an enormous value in looking for opportunities to make this technology available. And that's it.
Cool. Thank you, Kevin and Ronnie. Before taking questions from other participants, I have a quick question. So, Kevin, you showed us really examples of cutting edge technology that may be affordable, but based on both presentations, it looks like that these small farms can barely make a living. So where do they get even these 60 euros or 9,000 euros or whatever it is, actually get this equipment? Do they have access to loans? How do they manage getting that, and then training on using this technology, which may not be trivial? They still need that.
I have two answers for that. One is the implication of not having a lot of capital is that your payback time needs to be very short. And one of the reasons that I focused on the sensors and controls that I'm talking about is that they're not only technologies that pretty much any college or technical school or in some areas, somebody in the market who repairs cell phones could assemble from components that they can find, that they can access. A 60 euro sensor cluster that runs a drip irrigation system. Most of these farmers use drip irrigation because water is scarce. That saves them more than 60 euro in a season or increases productivity by more than 60 euro worth of product is absolutely worth them using. An aerial sensor cluster that is a balloon and somebody's smartphone, or a cheap cluster sensor that again can be assembled with open source technologies and open source code on the back end on any computer, a computer that's 15 years old, again, is affordable, and has a very short payback period and can provide large benefits. If you have a small co-op of farmers, maybe you get a regular drone. They're available for $1,000. Add the sensor cluster, it's about $2,000. That's out of range of an individual small farmer in the group that we're working with. It is certainly in range of half a dozen farmers. Similarly, the kind of technology that we're talking about with compost piles, where you have a large compost pile, you run drip line underneath, you blow air through the drip line, which means you don't have to take the time to turn the pile. It just sits there and composts. The time savings are enormous, completely worth it. If you put pipes under that compost pile, the heat that you get for heating water for agricultural applications or for domestic applications is free. Again, completely worth doing, completely affordable, very short payback. Anybody can do it pretty much anywhere in the world. So some of these are widely accessible, very low cost, have a very high return on that investment, because these are technologies that are widely available. This is one of the great advances in the technological revolution, but they're very simple and they're field maintainable. Now the tractor is designed, it's basically designed with developing countries and small farms in mind. It is clearly, if you're working a hectare, you're doing it by hand. And maybe you're using hand, there's a lot of low cost advanced tools for seeding, for weeding, for maintaining fields that make manual maintenance of the fields much more efficient. Again, you can grow more crops, you can have higher productivity. They make the work a lot easier. For the Ogun tractor, again, you are talking about a farm that's more like 10 hectares than 1 hectare, or where it's appropriate, or where you have a lot of social capital or social network among small farmers in a specific area, they can form a small cooperative and they can afford to purchase something like that and share it. So for a somewhat larger farm, or for a collective of farmers that are in the couple of hectare area, there's an opportunity for access to technology that, again, makes it very easy to enhance productivity. It doesn't reduce the amount of manual labor typically that's required. It does make that manual labor much more effective and makes your productivity very much higher. So that's our target for the kinds of technologies we're talking about.
And can I just add one thing, is that the state of California is very interested in, supporting agriculture and alleviating poverty. And so there may be public funds that are available even to farmers who are undocumented or don't have the sufficient experience to get agricultural loans. That's just, an observation.
And then one other thing I want to say is that there's some other things we're doing that I could talk about, but if we just present this at the workshop and we hand out these sensors, we're not done, because we need to basically go out, we need something like an agricultural extension agent. The follow-on is that we need to go out with these farmers, install it, help them set it up, show them how the interface works, be available if there are any technical issues, and most importantly, be tracking how these are used, how they could be better used, whether or not they are worth using, and refining, basically making technology choices going forward or refining designs going forward, so that we know that these are actually doing what we intend them to do. And basically, when we design these workshops going in with this demographic, we had to ask them, what is the way of getting this information that's most useful to you, and what kind of information out of the vast array of things that we could be talking about are most important to you? What are the things that concern you the most? And the follow-on on the back end is basically, is any of the stuff we're talking about actually going to help you?
Thanks. Any other questions? So do you think this technology could be available to places like Egypt?
The reason why I'm highlighting those technologies is because I think the answer is yes. And basically, the parts that we're talking, basically the components we're talking about are widely available. Some of them can be manufactured in country. They can certainly be designed and assembled in country. The return on some of those technologies, they can be customized to specific situations. You're not stuck with a standard design. You're not stuck with an infrastructure that can't be maintained in country or in a region. And it's adaptable to whatever crop or situation or climate you're trying to work in, or culture, to fit the flow of how people work and their agricultural situation. So flexible, low cost, standard components, manufacturing requirements that can easily be done within Egypt or parts of Egypt, widely adaptable. And so I do think that some of these are appropriate. Something like a tractor in an area where you don't have a lot of farmers working together and you have farms in the range of half a hectare. No, although there are other technologies that we talk about that are appropriate for farms that size. Again, affordable, easily manufactured, maintained in country, easily controlled by the farmers themselves.
And can either of you speak as to the water and energy use in using them? Is it increasing the efficiency or reducing water waste and energy waste?
It reduces. One of the technologies we're working with is a basically gravity flow, very low flow, high efficiency drip irrigation system. Drip irrigation has some cost issues. In California, you have to do it that way. In Egypt, I think because water costs are very low in many parts of the country, less of an issue, but anywhere in the country. So basically, you reduce energy requirements, you reduce water requirements, you have a very detailed understanding of how your plants are doing and any nutritional water requirements, any stresses. So you have you basically know what's happening with your field. A lot of farmers that are in a small field know a lot about already know a lot about their land and know about the crops that they're growing. However, understanding how their visual and experiential knowledge interacts with factors that enhance plant growth is still very useful for these guys. So resource savings, better productivity, higher efficiency, reduced labor, yes. Not all of these things are appropriate for small farms, especially when you're in the hectare range, but I think many of them are, and many of them are appropriate for small groups of farmers that can work together to develop this technology. For example, the aerial technology, basically a balloon, sensors, you can share that with a couple of dozen farms and get regular, very detailed understanding of what's going on.
Okay, thank you, Ronnie and Kevin. Do we have any other questions? I know it's very late in Egypt now, so maybe you're ready to go home to bed, but this is an opportunity to ask questions, and if not, we'll thank Kevin and Ronnie.
Actually, I want to ask a question, but it's not direct, have a direct relation with the presentation. but it's I'm so curious about, are there any access to use wastewater in organic agriculture in USA in general or California particular?
Ronnie, do you want to take that?
Well, I think, again, we would need to know more about soil conditions in Egypt, but at Whiskey Hill Farms, composting, and I don't remember if Kevin mentioned this or not, that when the farm was transferred, the soil was essentially dead. And applying compost, by taking in organic wastes, has done amazing things to enrich the soil. And of course, that also helps to retain more water. It's carbon sequestration. It's entirely, I don't know if farmers, small farmers, do that kind of composting, if it's, how much they have in the way of wastes, organic wastes. But I mean, that's one way of approaching the whole question of water conservation. We did try to find information about farming in Egypt, especially small farmers, and it was not all that easy. So it would help, to make a sort of better comparison and analysis if we had that kind of information. I don't know, Kevin.
I can answer your questions. I can talk a little bit about direct answer to your questions. The city of Watsonville in South County, which is within about a 80-kilometer range of a lot of the farms we're talking about, is starting to do what's called tertiary sewage treatment. So the water is fairly pure, down to the level of these kind of passive agricultural runoff beds that Whiskey Hill Farms is demonstrating. That is starting to be used as agricultural water. There are other parts of the state where sewer water is starting to be pumped into aquifers. One of the issues is that many cities like Santa Cruz use secondary treatment where it's not really agricultural water quality. And so there's a capital investment required to make sewage water clean enough to use. It is starting to happen. One of the issues in the United States, and I suspect in Egypt too, is that some of the return flows from agricultural operations and runoff have a lot of salts in them and a lot of nutrients. The nutrients cause environmental problems. The salts basically lead to salt accumulation in the soil. The salt content in the water is too high. One of the advantages of drip irrigation is that if it's applied properly in the root zone, it prevents the salts from reaching the plant roots and damaging growth. The short answer is yes, it is starting to happen. It is still not widespread, and it's expensive enough that it's starting to happen because California is becoming increasingly desperate about water resources, but it's still not a major factor. It is in a few areas, but it's not a factor everywhere.
Yeah, I think one of the issues, and Ronnie had answered that in the chat, is that water is still relatively cheap in California, and there's no incentive to invest in treating sewage water in a way that will make it compatible with reuse. It's changing slowly, particularly in Southern California, San Diego area, but it's still not very commonly used.
Right. And Central Valley, or our part, Monterey Bay, Salinas Valley, is another place where it's going to happen sooner than other parts of the state, because most of the state is fed by huge dams and water systems. Again, this part of California relies on rainfall. It's not tied into the larger irrigation system.
And the other thing to remember about California, that it's still the case that about 80% of water use in California is for irrigation, and that's from surface and groundwater. And the amount of water that's available, I think, from tertiary treatment of sewage water is much, much less. And so, and again, given the cost, I don't know what the current cost is, but you know, it's somewhere between, I don't know, $1 and $5 per acre foot.
Yeah.
Which would be what? It would be, you know, $2 to $10. Well, I can't convert it to meters, but
so one of the reasons why there's not more of it is that there's a reason why the city of Santa Cruz and a lot of cities use inferior treatment, because it's more expensive to treat the water better. One of the things that is changing, which might increase the reuse of water, is that the state is imposing very strict standards on the level of nutrients and biological activity that's allowed in runoff from farms. And one of the advantages of the REED system that we're talking about is that it's a very cheap, very cheap passive way of doing high quality sewage treatment for agricultural runoff. The other thing when we get to compost is the state is also imposing strict restrictions on landfilling agricultural waste and food waste. And so at least in the short to medium term, there's a huge surplus of organic waste that was going into the garbage, basically, that agricultural operations now need to find a way to use. That happens to work very well with some of the techniques that Whiskey Hill Farms and organic farmers are applying to improve soil health. So there's a feedstock that's cheap and available to a lot of the farmers in our area.
Cool, thank you. Since we are out of time, unless there's any other urgent questions, let's thank Ronnie and Kevin again. And as I said, we'll have their PowerPoints or contact information if anybody has further questions. It looks like Asma has her hand up. Go ahead, Asma.
Thanks a lot for all the presentation. I would like to ask you, is that any policy or regulation control the virtual water according to the type of crops in California especially, or this is free for any crops for small farmer? I mean, it's free for any kinds of crops growing or seasonal, or is that any control about that?
Yes and no. There isn't a state mandate for growing a particular kind of crop, but the senior water rights regime, and until very recently, there were no controls on groundwater pumping. That's changing now because a lot of areas in the state the aquifers have been overpumped during the drought because of uncontrolled groundwater withdrawals. For surface water, because of the senior water rights situation, a lot of the surface water that's available is controlled by large farms. And they're growing things like cotton or rice for export. Their water is heavily subsidized by the federal government, unlike areas like Monterey Bay, where there isn't a lot of public water infrastructure. And so the de facto result of that is that in the Southwest, where there are extreme water shortages, in Arizona, there are people that are growing lettuce. In Northern California, in the middle of a drought, there are open rice paddies. They're all running on subsidized water. A lot of forage crops, hay, alfalfa, are grown for export. So we export hay grown with subsidized water to China and bring in expensive electronics. There's some economic patterns that wouldn't be possible if in a system that didn't have heavily subsidized water that favors large established farms who can grow whatever they want.
As a former politics professor, again, it's very important to understand the politics in California. The cheap water, much of California is supplied with water through two very large projects that move water from the Northern California and the mountains to the rest of the state throughout the Central Valley, which is where there's a lot of this agriculture that Kevin was referring to, and to the urban areas in the southern part of the state. And these systems were basically built to encourage the growth of agriculture and, and the production of various kinds of crops, some of them for export out of the state. But the lobbies, that is to say, the groups that determine what the state's policy is, are very powerful. Farmers have a very powerful, what we call lobbies, in terms
Large
of
farmers.
water districts. What?
Large farmers.
Large farmers, yeah. And since a lot of this water law would have to be changed through the legislature, the California legislature, it's very difficult to get anything like that through. And there's a whole cult of the farmer across the United States, which is sort of the smaller yeoman farmer is the representative of the cult. But in fact, most of the farms, as I pointed out, are quite large. They represent the biggest part of the agricultural sector. And so it's a kind of a myth. And, again, I don't know about similar things in Egypt, but it's very, very difficult to dislodge that, and changing the pricing of water, which would drive out more water intensive crops and sort of shift production to more concern about providing food and perhaps value would be very difficult to do. So, that's really one of the primary obstacles, which is why, in a way, the technology is almost secondary to the politics, or it is secondary to the politics. So it's always important to be cognizant of the social science side of these questions.
If you'll indulge me, I want to talk a little bit about one of the things that's motivating us with this is as supply chains, as kind of global supply chains become more uncertain, and the possibility of disruptions becomes more possible. One of the things that people are starting to think about in the United States is the capacity of regional food systems to provide at least part of the food requirements of the local population. And there's two things about that. One is there's a question of how much food could you grow locally for local consumption if you're serious. In the case of Monterey Bay, we're very fortunate that that capacity is very high, even though most of the land is going to strawberries, artichokes, and other export crops. The other thing about it is that if you can establish very short supply chains from farmers to stores and markets and restaurants, you not only provide farmers with a larger margin because they're not dealing with distributors and wholesalers, you also have a very short supply chain providing local food to local markets. It's very politically popular. Again, like the idea of small farmers is the example of the American farmer. It's still a very small percentage of food production, even in areas like Monterey Bay, where Silicon Valley, San Francisco, a lot of people want something like that, just as there are people in Europe who want organic food. And so Egypt ends up exporting organic produce to Europe instead of using it domestically. One of the things that happened during COVID that was very interesting to us and that kind of motivated us to start thinking about technology transfer to regional small farmers is that there was a period at the beginning of the COVID epidemic in the United States where some of these larger processors and longer supply chains broke down, and there were spot shortages of food in the United States. What we expected was that the local food supply chains, the short ones, would be very resilient. And what we found was that they were in some cases, but in some cases they were not, because farmers had contracts with a store or a restaurant, and the restaurant went out of business, or the store shut down, and they didn't have a market. And so all over the United States, where there were longer supply chains, farmers were plowing their crops under. And some of that happened in our part of the world as well. I think one of the challenges is developing that robust local short supply chain that can reliably provide food, and because it's a short supply chain, can provide enough money to small farmers that they can afford to do that.
Okay, thank you. Thank you.
Okay, well, thank you, everybody. And the recording is available. Ronnie put the contact information on the chat. So if you've got follow-up questions, you can reach Ronnie and Kevin through that email. And I will see you next Tuesday. And let's thank Ronnie and Kevin again. And good night to you guys. And have a nice day, Ronnie and Kevin.
Thank you.
And thank you so much. We appreciate being invited.
Yes.
Thank you so much, Professor, for this amazing session. It's really one of the most interesting sessions we had through the web. Thank
You're
you.
welcome.
Bye. Goodbye, everyone. Good night.
Bye.
Okay, thank you and
Good
goodbye.
night. Thank you so much. Good night.